In Lecture 12, we're going to talk about square planar compounds and look at an idea called the trans effect. I would like you to finish reading Chapter 5 and start reading Chapter 6. In the next lecture, we will talk about applications of coordination compounds, and then at the end of the semester, we will spend a little time learning about solid-state compounds and their applications. This is your next homework set, and it will be due by the end of this week. We've looked at substitution mechanisms in octahedral complexes. Remember that substitution in octahedral complexes occur by a dissociative mechanism. In square planar compounds, this substitution occurs by an associative mechanism, where you will form a 5-coordinate intermediate. Most square planar complexes form with D8 metal cations such as Pt2+, Pd2+, N2+, and Au3+. So there's a very small number of metals that you will look at when it comes to the trans effect. The trans effect is a kinetic idea. It defines the relationship between the rate of substitution on a square planar complex and the nature of the transligand, or of the ligand trans to the ligand being displaced. Now, we'll be looking at a number of examples throughout the rest of this lecture, but it should be known that non-labile ligands in square planar complexes can be ranked in an order that have been determined empirically. That's by experiment. The ability of a ligand to displace another ligand trans to it is known as the transdirecting ability. This is much like the spectrochemical series. You need to memorize this. It will help you answer many questions. At the high end, ligands like Cn- and CO- will displace transligands very well, whereas at the other end, NH3 and H2O displace transligands poorly. And in the middle you have, that area of gray where the ligands could displace poorly or not so poorly. The closer to the CO and Cn- end that the ligand is, the better it will displace the transligands. We will be looking at the displacement of chloroligands in this section. Now we will be forming PtCl2 NH3NO2 1- from PtCl4 2- as an example. The trans effect will be very useful for helping us make the two different isomers of this compound, the cis and trans forms. Empirically, the chloroligands are the easiest to displace in Pt2+ complexes. When looking at the substitution of PtCl4-, the transdirecting ability of substituted ligands is used to predict which products will form during the reaction. We will look at two different reaction schemes now. So let's start off with PtCl4 2-, and we will add NH3 and remove one of the Cl's. Since all 4 Cl's are exactly the same, we pick one at random and replace it with NH3. Since we're losing a Cl-, we must reduce the charge on the overall complex by 1. So the new complex should have only a 1- charge. That's what I've done in this step. Now, thinking about the trans effect and the transdirecting series, we have to decide which ligand is going to be a better transdirector, NH3 or Cl. if we look back, we see that Cl- displaces the ligand trans to it much better than NH3. Therefore, we should use one of these Cl's to displace the one trans to it. So I'll pick this one. It will remove this Cl. So now let's add NO2- and remove that Cl. What you should have is two chloros that are cis to one another, and the NH3 and NO2- that are cis to one another. The charge should not change on the complex since you're removing a Cl- and replacing it with NO2-. This is the final product from this reaction series. Now let's take and look at another scheme, starting off with PtCl4 2-. This time we're going to add NO2- and remove one Cl-. So that's what we're doing. We can choose any of the four chloroligands to replace with NO2-, and that's what I did. Notice that the charge didn't change because you're replacing an anionic ligand with another anionic ligand with the same charge. Now we have to decide whether NO2- or Cl- is the better trans director. If you look back in your notes, you will notice that NO2- is the better trans director, so it should displace this chloroligand. Let's add some NH3 and remove the Cl-. That should reduce the charge on the ion by 1, and you should get this compound. Notice by just knowing the order in which to add the ligands, you can make two different compounds. You can make either the cis compound or the trans compound. So now we're going to look at two examples. We're going to predict the products of the following reactions. In the first reaction, you have CO trans to Cl, and you have SCN trans to Cl. Think for a minute. Which ligand is going to be the better trans director, CO or SCN? If you look at the trans-directing series, CO should be the better trans director, so this Cl should be removed and should be replaced with NH3. In the second example, we have Cl trans to Cl and Br trans to Cl, and we want to add NH3. Which is the better trans director, Br or Cl? In this case, Br is the better trans director. So it will displace that Cl and replace it with NH3. And these are the two products that you should get, just like I suggested earlier. Remember, since you're replacing a Cl- on this complex with NH3, a neutral ligand, you need to reduce the charge on the overall compound by 1, making it a neutral compound. The same goes for this complex. Since you're removing Cl- and replacing it with NH3, the overall charge on the complex should be 1- now. Now let's rationalize the trans effect.